Aloha, Stephen Pike again, Assistant Professor, Merchant Marine Academy. We're going to continue on where we left off on our refrigeration uh, example. First thing I want to do is clean up our display a little bit so we make sure we're in the A mode for editing. And let's go ahead and select all of our little text items. We'll make them a little bit bigger so they're easier to read. And properties, text size, let's go to 18, see how that looks. Yeah, it looks all right. So now we need to move these around a little bit. And, well, actually, they're fine. So what we want to do also is take our input items and make them a different color so they stand out. We'll make those red. I like a little darker red. So I do that. And make it bold. All right. So now we've got that. And one more thing, let's put circles around the numbers so they stand out a little bit better. It transparent, and we'll make the ring a little bit bolder. That looks okay. Make a couple copies. Let's see, copy 1, 2, 3. Put one over the 2. Find that 3. Same thing with the 4. These are just little things to show you ways you can make a plain diagram into a much better looking one. So we've got that. So let's go ahead and take the rest of our inputs and put them all on this screen. So let's go back here, and we had P2. So we'll comment that out. Subcooling, comment that out, and that should be it. So add input variable 18 red. Okay, we want P2 and we also want subcooling. So input variable, temperature, subcooling. Okay. I'll put P2. Actually, let's keep all of those in one place. And we'll actually make a copy of this. And paste it. Oh, not what I wanted. copy, paste, put that up here. So we've got all of our inputs in one place. We'll change this to an output variable, and we want it to be black again. So we'll go back to black. And we also want to make it not bold, so it blends with the others. All right, so now calculate after we change modes. And that's because we need 141 here and 5 here. Okay, and there we go. Back to where we were. But now we've got all of our inputs in one spot. We can neaten this up a little bit using going back to the A mode, add mode. This allows us to align the left sides, what we want to do here, and we want to space it evenly. And there we go. So, next thing we want to do, let's determine how much we're removing per pound. Actually, let's go back to this one more thing here. Cancel that. So we want to select all of these. You notice they were disappearing. And once in a while you'll find you get an artifact that you just need to cut it out. So we do that. And there's another one. Okay. Yeah, it looks like there's no more. How about down here? Nope. Alright, so we'll select all of our text. Output text. And what we'll do is, if you noticed before, some of them disappeared. So we'll go to Properties, and we'll click off Show Only After Calculations. We want them to show all the time. So we've got that. Now, they're still showing. Excellent. And we can calculate. Notice they're no longer gray, they're black. That's good. That means it's a calculated value. We can look at our items here. Nothing major. Again, we got our arrays. There we go. Back to where we were. Just have a little bit nicer output here. So the next thing we want to do is see, all right, so how much heat are we rejecting per pound here? And how much work are we having to do on it? And how much heat are we rejecting from the cycle over here? So what we want to do is, we'll say 5. Determine heat absorbed. Let's say specific heat. Absorbed in the evaporator. Work of the compressor. And heat rejected in the condenser. So, Q evap equals the change in enthalpy. So that's going to be H4, no, H5, H1, excuse me, minus H4 W compressor is going to equal the change in enthalpy across the compressor, which is H2 minus H1, and Q condenser is going to equal H2 minus H3. Let's see what that gives us. And now we've got our solution. So we got suggested units because we didn't assign units. So let's go ahead and just right click and accept the units. No unit problems detected. Everything looks good. So let's do a check. And let's say, so the heat rejected in the condenser, Q rejected, should equal Q condenser. It should also equal the heat of the evaporator, absorption, plus the heat of the work, the heat put into the compressor. So let's see if that check is satisfactory. And look at that, 6202, 6202. So it's always good to have an alternative calculation you can use to check and see if what you're getting in your initial calculation checks out with an alternative way of calculating the same value. So what we can do now is we can add those values to the diagram window. So let's go to A. Let's say we want to do an output variable, and let's use a different color. Let's use green. Okay. And we'll have bold and italic. And what we're going to do is the heat of the evaporator. Okay. And let's do another one. Output. And we'll put, we need the work of the compressor. Okay. Put that up here. And then the last one we want, oh, we don't want to do that. So notice this is still highlighted. If I change it, it's going to change this value here. I don't want to do that. So now it's not highlighted. We can select an output variable, and we want the Q condenser. Okay. And I'm actually thinking our text is a little bit too big for this. So we'll go through and we'll just select everything we have text for. And properties, and we'll make it 14. Yeah, that's a little better. All right, so we can also tighten this up a little bit. We'll just move one of these up and do the thing again. So you just gotta be careful. You can select by a group by just surrounding it. And we want to do the realignment thing again. The left side, space equally. Okay. All right, that looks a little bit neater. So now we looked at how much heat we're removing. One final thing I want to do is let's make an assumption that our heat load is 2 tons. If the load is 2 refrigeration tons, determine the mass flow rate. So we want to determine mass flow rate, so that's m dot, and our mass flow rate throughout the refrigeration side of the system, the working fluid, is the same, so we're just going to use m dot. That has to equal the so the mass flow rate has to equal the rate of cooling in refrigeration tons, and we said 2 refrigeration tons, and I'm going to convert that to 24,000 BTUs per hour, because that 12,000 BTUs per hour is 1 refrigeration ton, divided by the evaporation rate, U EVAP. Let's see what we get. So we need rate accept those units, and we end up with 500 pounds per hour, as you saw. And that's for R12. So the other thing that I would like to do, so let's do a coefficient of performance as well. So let's do a coefficient of performance. That's an important measure for refrigeration systems. It's basically how much refrigeration we get, how much heat we move for how much work we put in. So coefficient of performance, let's do 7. Determine the coefficient of performance. COP is a common abbreviation, and we'll actually use that for our variable name. All right, so the way we determine the COP, we'll call it COP. So one other note for ease. You can use anything beginning with a letter can be, or a Greek, well, letter can be used as a variable. Greek letters are spelled out. But you can't use a capital letter and a small letter as a different variable. So a capital V and a small v, ease is going to look at as the same variable, just as a note of caution. It's not case sensitive in its variable naming system. So coefficient of performance equals the heat we remove in the evaporator divided by the work. that we need to remove that heat. Let's see what we end up with there. COP 3.176, not too bad. So now, this is R12. And we'll stop here for now. What we'll do is we'll add one more thing over here. We'll add COP. Alright, so we'll put an output variable, COP. It's right at the top because it's alphabetical. That's convenient. We'll put that right up here. And we'll save that and call it a day for this one.